And for simplicity, let's talk about d-regular graphs. This basically means we are interested in graphs where every node has degree d, which basically means every node has exactly d connections. This is just for simplicity. Everything also works for kind of different graphs, more interesting ones. But let's think for now just about graphs where every node has degree exactly d, which means it has d edges adjacent to it. So now we can start asking about what are some eigenvalues and eigenvectors of this d-regular graph G. And let's think, right? So here is our equation that we'd like to solve. A is our adjacency matrix, X will be our eigenvector, and lambda is the corresponding eigenvalue. And basically all we are asking is, what are some solutions to this matrix equation, where A is given, while we want to find lambda and X. So the question is, what is lambda, what is X? So let's, for example, try X equals all ones, right? So let's think that we want to try out whether a vector of all ones is an eigenvector of our adjacency matrix. Actually, if we think about it, what happens is simply we say, okay, what is A times X? We already know that A times X is simply for every node. They ask, what are the labels of my neighbors? And they sum up these labels, right? Since in our d-regular graph, every node has exactly d neighbors, and all the neighbors have labels of 1, this basically means that after every node sums the values of its neighbors, the value of that given node is d, right? So this means that A times X equals a vector of all entries have value d. So now this means is we basically solved our solution, right? We solved our eigenvalue problem, because we say that this is now d, lambda times X, right? Where lambda equals d, and X is a vector of all ones, right? So we have just solved our eigenvalue problem, and what we have learned is that we found an eigenpair of our adjacency matrix A of graph G, simply that X is a vector of all ones, is an eigenvector, and the corresponding eigenvalue is lambda with value d. So now we can start asking, what if our d-regular graph, for example, is not connected, right? So in previous case, we basically made this implicit assumption that every node has degree d and that our graph is connected. So now let's start thinking, what if our graph is not connected? Let's think about that our graph has two connected components and each one is d-regular. So for example, here on the right, I have an example of a two-regular graph where we have two connected components, right? Basically, we have kind of two separate graphs that are not connected with each other, and every node has degree 2, so this is a two-regular graph. So now the question is, what are some eigenvectors, eigenvalues of this graph here on the right? And if we think about the following, basically, we can use the intuition from the previous slide where we can say, okay, let's put all the values of 1 on all the nodes in the component A, and let's put all the zeros on the nodes in the component B in our graph G up here. So if we go do this, what do we learn? So for example, if we try out the vector x prime that has entries with value 1 for all the nodes in A and entries of 0 for all the nodes in B, then if we multiply A times x, basically what we obtain is we obtain a vector of this. This is for the nodes in A, and we obtain a vector or a subpart of all zeros for the components in B, right? In A, all the nodes have entry 1, so when I sum them up, I get the value of D. In the component B, all the nodes have value 0, so when I sum them up, I get 0. Right? But what we see is basically that we again found an eigenpair, right? The eigenvalue is still D, and the corresponding vector is here. Similarly, right, kind of analogously or symmetrically, we can do the same thing where we put all the values 0 or label 0 to the nodes in A, and all the values 1 to the nodes in B. And again, if we do the A times x double prime now, we obtain basically the same vector. And again, we have the eigenvalue of D. So what we have learned is basically that in both cases, we have now two different eigenvectors. The first one that has entries 1 and then all the entries 0. The other one when first we have zeros and then we have ones. And in both cases, the corresponding eigenvalue equals to D. So now if we basically use a bit of intuition, what we have learned is if I have a d-regular graph that has two connected components, then I have the eigenvalue lambda equals d of multiplicity 2, which means there are two eigenvectors corresponding to the eigenvalue of d. The first corresponding eigenvector is the x prime, and the second corresponding eigenvector is x double prime. So now, if we kind of intuitively think about this and ask, okay, what would happen if our graph with these components A and B would be barely connected? So what if we would have the case, as I have it here on the right, where I have a few edges crossing between A and B? Right, then kind of our intuition would be that maybe there would be a bit of a difference between these eigenvalues, right? So I wouldn't now have eigenvalue of D with multiplicity 2, but I would have eigenvalues lambda 1 and lambda 2 that are about the same, right? They are about similar because for all practical purposes, in a sense, our graph has almost two connected components, right? I have just a few edges crossing from side A to side B, but kind of it almost looks like separate components, just that there is an edge connecting them or something, right? So we would expect that the two eigenvalues will be about the same, or will have similar magnitude, and this also means that the vectors x and x double prime will kind of be our eigenvectors, right? So basically, if our graph is disconnected, we already know what the eigenvectors will be. If the graph will be barely connected, the eigenvectors, we hope, won't change too much.